Hey everyone, today we are going to finally start the diffusion model, which is currently basically your state-of-the-art generative model for all sorts of tasks, whether or not you're working with images or audio or really a lot of other types of data. So of course, like I always do, before we actually implement the diffusion model, I need to actually derive some of the math for you. And I think it's especially important here because the formulas for diffusion look very weird and not exactly intuitive of where they come from. And the two main formulas that typically get thrown at you, but you don't really know where they're coming from, are these two. First is, so this is the original diffusion paper. So there you go, DDPM paper. And the main equations we care about is here, equation 4, this one right here. And the other equation we care about is this one right here. And the question is, where does all this stuff come from? You kind of just implement it and you have it, but it's probably better to know exactly what's going on. So we're going to get there. Now, we actually haven't talked about diffusion yet. So let's go ahead and just give a little bit of an idea of what's going on. A diffusion model is actually a lot like a GAN model. So in the same way, in a GAN, we generate data, right? That's the entire purpose of a GAN. Now, the problem with the GAN, if you remember, the way we generate data, the way the generator works in a GAN is we provide some noise, typically some Gaussian noise, to our generator, and the generator then takes that noise and creates a image, audio, whatever you want it to do. The problem with this GAN setup is essentially this. You are essentially in one forward pass going from noise to data. And that's actually a lot to ask for a neural network to do. And it could be unstable. It could be a challenging thing to do. So it's not exactly the best way, going straight from noise all the way to your data in one forward pass. And so what the diffusion model does is, instead of trying to go from your noise to data in one forward pass, what if we iteratively build our image or build our data from noise? So here's the main idea for diffusion. There's plenty of really great videos on YouTube that you can find for this stuff as well. So just go ahead and take a look at them. But the main idea here is you start with some data. We're doing images, so or we will be working with images. So here we go. We have a picture of a dog, and we're going to iteratively add some noise to the image, right? So as you add noise, one step at a time. So time step 1, time step 2, up to t time steps. As you add noise to an image, then of course, at some point, you're just going to have a bunch of noise. That's all that's left over, right? The noise has overwhelmed the original image. So adding noise is no problem. That's pretty standard, not too challenging. The difficult part is taking this noise and reversing the process. So we're going to have a neural network learn to essentially take xt and go to xt minus 1, go from xt minus 1 to xt minus 2, ... and essentially estimate the image. So what it's really doing is the neural network is learning to estimate the noise, right? How much noise was added at a specific time step. That's the key principle we'll be working with. Now, there's one small addition, kind of an additional thing that we need to remember or think about, and that's when we add noise one step at a time, we don't just add Gaussian noise, like just some we have something known as a noise scheduler that determines how much noise we want to add. And essentially the noise scheduler, the noise we add is always just Gaussian noise. So it's just going to be regular Gaussian noise. And it's going to be zero-centered Gaussian noise. So we kind of vary above or below 0. But what we can control is the variance of the noise, right? The variance is essentially your spread of the distribution. The larger the variance, the heavier amount of noise that you'll be adding at that specific time step. So our goal will be to use a noise scheduler, which is provided ahead of time, which says how much noise do we want to add at every single time step. So that's something we have ahead of time. It's noted or denoted by the letter beta, right? I'm using beta as that. So let's go ahead and kind of take this principle here, break it apart, and see what we want. One of the key ideas, though, another key idea, is notice here the probability of t of xt, right? The distribution should be standard normal. It should be a 0, 1 Gaussian distribution. So that's going to be one other kind of thing we have to keep in mind. As we go from x0 to x1 to x2 to ... we want to make sure that the distribution of the pixels or whatever data you're working with has a variance of 1, right? So we want to make sure we don't change the variance of the data, essentially. This is especially crucial just because as we are adding noise, if you keep adding noise without adjusting this, you'll end up with something known as a variance explosion, right? So there will be way too much variance, the values will be way too large of a range, and the neural network will really struggle reversing that process. So we want to make sure two things. As we add noise, we add it according to some scheduler, and then according to that scheduler, as we add the noise, we want to make sure that our variance is always 1. So let's go ahead and start with the forward diffusion process first, the noising process, and then we'll come back to the reverse process and implement that as well. And that'll give us our two main formulas that we'll be working with for the rest of basically our implementations in the future. So let's just pretend right now our data, so we're doing the forward process now, forward process. Let's say we have x0, that's our data, the original data, time step 0. And just for sanity's sake, let's just say it has it's just some normal distribution. It doesn't have to be, but let's just say it is, just because it makes the math a little bit simpler. Let's have a mu, so it has any arbitrary mean, we don't really care. And let's just say the variance of x0 is 1, just so we can see, if we don't leave it as 1, then we'll just always have an extra constant in our derivation, just easier to leave it this way. So this is our first step. And also, we have something known as the variance scheduler, which we'll just call it this, right? So t, and this is going to produce some beta t, and beta t is the variance of the noise that we're going to add at a specific step. So that's going to mean if epsilon is the noise we want to add, it'll come from some normal. We typically leave the mean of the noise as 0, but it'll have some beta t amount of variance. So that's the key idea. So step 1 is, how do we add noise to x0, basically adding epsilon to x0, but ensure that we still have a 1 variance at the end, right? Okay, so let's go ahead and set it up. So x1 is going to be the sum of our original data, right? It's going to be equal to x0 plus our epsilon, right? It's going to be the sum of these two. We're adding our noise to our x0, but we're going to add some constants here, a and b. And a and b are just going to be scaling constants, and this is the sum of two Gaussian distributions, or two distributions in this case. And a and b are just going to be constants. So a, b is element, right? It's going to be some constant on the real line. And so let's go ahead and see what a and b should be. Let's start with b. It's a little bit easier. So what is b? So what is b, right, is the question. Okay, so to figure out what a and b should be, we need to remember one important fact that's going to come up over and over again, and that's our variance formula. So again, think back to your original statistics class where you saw the variance of a constant a times x is the same as a squared times the variance of x, right? So this is a standard formula from statistics. And epsilon, right? Epsilon here, what we want is normal 0 beta t. That's what we want. Now, the way we typically do this isn't starting here. We're going to say epsilon is normal 0, 1. Let's just keep it simple. It's normal 0, 1. But what we want is normal 0 beta t. So how do we get there? Well, if we want our variance of epsilon, so right now the variance of epsilon is equal to 1, we want variance of epsilon to equal to beta t. That's what we want. So let's just go ahead and use our formula, right? So if we want the variance to be beta t, the variance of epsilon to be beta t, that means if we do epsilon times the square root of beta t, the variance of this, let's just take that for example, the variance of epsilon times the square root of beta t. Well, by our formula, if we pull beta t is just a constant, right, that comes from a scheduler. So if we just pull beta t out, or the square root of beta t out, then we have to square it, right? So this is the same as the beta t squared, right? Beta t squared, or square root of beta t squared, times the variance of epsilon, which is just beta t. And the variance of epsilon, if epsilon is starting from a normal 0, 1, then that's just 1, right? Times 1. So that's equal to beta t. Therefore, our constant here, all we need to do is take epsilon, which is normal 0, 1, and multiply by our scaling factor, square root of beta t, and that will give us the actual epsilon we're interested in, right? So this will produce So if epsilon is normal 0, 1, then square root beta t epsilon will be normal 0 beta t, which is exactly what we want. So it's just a trick. If you remember, if you think back to variational autoencoders, this is also the same as the reparameterization trick, right, that we saw there, where you essentially move the stochastic node out and kind of do this multiplicative operation, but that's okay, right? We're going to kind of leave it at that. So that gives us our first constant. That means x1 is going to be equal to a, we haven't solved for a yet, so that's ax0, plus square root beta, let's say 1. We're adding one step of noise, so it's going to be whatever the beta 1 is. Beta 1, and it's going to be epsilon, just like that. So that's our first setup, and this gives us the epsilon that we actually want, right? The variance that we actually want to add to our data. But we need to make sure we scale x0 such that the final x1 has a variance of 1. So let's go ahead and do that. The variance of x1, right? Variance of x1, which is equal to the variance of all this stuff on the inside, ax0 plus square root beta 1 epsilon. We want this to equal to 1. So let's just solve for a, right? It's just a simple equation. So if you remember, this is the variance of something plus something. So if you have the variance of, let's say, p plus q, that's the same as the variance of p plus the variance of q plus 2 times the covariance of pq, right? Covariance. Now, in this case, this term here, which we don't really care about the constant, so just epsilon. Epsilon is a randomly sampled thing, right? We just randomly sampled it. And so that means something that's random has no covariance with something else, right? Because they're independent of each other. So because they're independent, we don't really care about this covariance term, and we're just left with these two here. So that means we can just rewrite this as the variance of ax0 plus the, and of course, this is going to be the variance of square root beta 1 epsilon, just like that. And like our variance rule from before, that's going to be a squared variance of x0 plus the square root beta 1 comes out, giving us just beta 1 variance of epsilon. And this is why I selected, so just for simplicity, I made the x0 has a variance of 1, right? That's why I selected it that way, just to make this math a little bit simpler. So this term is just 1. And we know epsilon is just standard normal, so it's 0, 1. So this is also 1, right? The variance of these two terms, which means we have a squared plus beta 1 is equal to 1, right? The final variance we want is 1. So that means a is equal to the square root of 1 minus beta 1. And this is our other constant, right? There we go. And so that means our x1 term is going to equal to the square root of 1 minus beta 1. And it's going to be x0 plus square root of beta 1 epsilon. And that's our effective formula. That's what we want. Now, more generically, this is for time step 1. We want it for any arbitrary time step. So we can do xt, so the tth time step of noising on our image is equal to 1 minus beta t, whatever the variance scheduler decided the variance of that current noise we're adding at that time step t, times x t minus 1, right, the previous time step, plus square root beta t epsilon. And so there is our first major formula that's not directly used in diffusion, but is a core part of what we're trying to do, right? So we can say that xt is basically a weighted sum of our xt minus 1 and epsilon, and the weighting ensures that xt, right, so the variance of xt will also be equal to 1. This way we avoid any kind of a variance explosion when kind of, adding all these perturbations to our data. Now, we can actually write this in one other way, and this is a kind of a key idea. Let's kind of look at it this way. Let's say we have some y is equal to some mu plus sigma epsilon. And let's say epsilon, right, is normal 0, 1. Right? So if epsilon is normal 0, 1, what is the distribution of y? Well, if we take normal 0, 1, multiply by sigma, that means the variance, so the variance, let's do it one piece at a time, sigma epsilon is equal to sigma squared variance of epsilon. And that's just equal to sigma squared, right? Because the variance of epsilon was just 1, as we indicated. So that means the variance of this is sigma squared, so that's fine. What's the variance of y then? So the variance of y is equal to the variance of mu plus sigma epsilon. Now, mu is just a constant. There's no variance. So that means the variance of a plus something, our random variable, is just the variance of that random variable, right? So we don't actually care about mu because it's a constant. It has no effect. So that means the variance of y is just equal to the variance of sigma epsilon, which we just showed earlier was sigma squared. On the other hand, what is the expectation or the mean of y? Well, that's going to be the expectation of mu plus sigma epsilon. And so that's going to give us the expectation of mu plus the expectation of sigma epsilon. Now, the expectation of something times something, this sigma is just a constant, so we can actually pull it out. So this is just sigma, and then we'll have the expectation of epsilon. But remember, the expectation or the mean of epsilon is 0, right? So this term is just 0. So all we're left with is this. So this means the variance, the y is a normal mu, right? The expectation of mu is just a constant, so this is just mu. It's just going to be a mu sigma squared distribution. And so all I'm trying to get at here is that if you take some noise here, that's 0, 1 in this case, scale it by a constant, and then add a constant, you end up with something like this. Well, is that not what we're doing here? We're taking some epsilon, scaling it by some constant, and then adding some constant. And this is a constant because remember, to create xt, we input xt minus 1. So xt minus 1 is already known, so it is a constant. So that means xt here, comes from a normal distribution that has a mean of all of this stuff here, right? The thing we added is the mean, just like we had here, right? We added mu, so that's why the mean was mu. So let's go ahead and write that. That's the square root of 1 minus beta t x t minus 1, and a variance of this thing squared, right? It's the variance of this thing squared, the thing we multiplied by. Again, for the same reason, we multiplied by sigma, so the variance became sigma squared. We multiplied by the square root of beta t, so the variance is just beta t. And so this is a key takeaway formula of kind of matching a little bit to the paper of where all this stuff comes from. So xt essentially is coming from this normal distribution. So this, more specifically, this notation is fine, but the way you'll actually see it in the paper is instead of just writing xt, you'll see it written like this. Q xt given xt minus 1, right? So going from xt minus 1 to xt has this distribution. And so that kind of solves our first step of this derivation. So if we look here, I don't actually remember if they give the specific one. Yeah, it looks like they don't. They give the full form from x0 to xt. So let's just keep going and we will come back to this again. So this is all well and good, but there's actually one slight problem. Not really a problem. Everything would be fine if we use this method. It's just not efficient. And why is it not efficient? Because we want to add, let's say, 1 step of noise, 2 steps of noise, 3 steps of noise. But this means if we want to add 100 steps of noise, we have to for loop, right? We have to add 1 step of noise over and over again, just repeating this formula over and over again for 100 times. And the question is, can we do a little bit faster? Like, can we just add noise once? Because we're adding Gaussian noise, right? In the end, it's just Gaussian noise. We're just adding Gaussian noise over and over again. And if we're just adding Gaussian noise a bunch of times over and over again, then I know what the final Gaussian noise would be, right? I know all the properties of a Gaussian distribution. So whether or not I add 1 Gaussian distribution or 100 of them, it doesn't make a difference. I just need to compute the exact formula of adding t steps worth of noise. So now we're going to do the generic form of, instead of just adding 1 step of noise going from xt minus 1 to xt, we're going to say what happens if you add all t steps of noise. So starting at x0 and saying, I want to add 50 steps worth of noise, or I want to add 100 steps worth of noise, or whatever it may be. And so that's the key idea. And that's basically what this is, right? Where we want to show that we go from x0 to xt in one step. And so let's go ahead and see where this formula comes from. So now we're going to be doing a more efficient forward pass, essentially. Now to pull this off, they introduced some new variables. You don't know exactly why we need them yet, but you'll see why a little bit later. It's mostly just for efficiency and for shorthandedness. So we create a new variable called alpha t, and it's just 1 minus beta t. So again, beta t is the same as before. It's the variance determined by our scheduler. So there you go. So alpha t is 1 minus beta t. And we also create a alpha hat t, and this is just going to be the product of s equals 1 to t of alpha t. So it's just the, the product all up to all t terms. And so what does that mean? That means, let's say alpha 2 is equal to alpha hat 2. It's going to be alpha 1 times alpha 2, because we're going to do from s equals 1 to s equals t, and in that case it's 2. So it's 1 and 2. And then we can rewrite this as 1 minus beta 1, 1 minus beta 2, just like that. So that's basically how this hat notation works. And so we're going to be using this. So let's start with what we had earlier. We had xt is equal to square root 1 minus beta t x t minus 1 plus square root beta t epsilon, right? That's what we started with. Now to do this, what we need to do is let's go ahead and write the recursive form. So we have a form for xt here, but we have an xt minus 1 inside the xt. So let's see if we can write xt minus 1 out, substitute it in, and just see a pattern. And that pattern will basically show us what we want. So let's also write xt minus 1 will similarly be square root 1 minus beta, but now it's going to be, let's write that a little bit better, beta. But instead of beta t, it's going to be beta t minus 1. We're going to reach into x t minus 2 plus square root beta t minus 1 epsilon. So we've basically re-indexed everything 1 back, because it's the formula is the same no matter what time step we're at. And so let's go ahead and take this and plug it into here, right? So that means xt is equal to, so we'll first have what we had before, square root 1 minus beta t. That's the first step. After that, what we're going to do is and actually, let's go ahead and just do a little bit of a shorthand here. Let's make this simpler. Let's say this 1 minus beta t, I already called it alpha t up here, right? 1 minus beta t. So this is going to be the square root of alpha t, x t minus 1, plus square root of, so if alpha t is 1 minus beta t, that means beta t, right, is going to be 1 minus alpha t. So it's going to be 1 minus alpha t. So there we go. And it's going to be epsilon. And then this one's similarly going to be the square root of alpha t minus 1 x t minus 2 plus square root 1 minus alpha t minus 1 epsilon, just like that. Again, it's just to get the notation right, and you'll see exactly why this is important in just a bit. So now let's go ahead and take basically this stuff right here, which is xt minus 1, and just plug it in there. So that means xt is going to equal to the square root of alpha t, right? Square root of alpha t. And then xt minus 1, we have our form for it. So that's going to be square root alpha t minus 1 x t minus 2 plus square root alpha t and then minus 1. And we're going to have our epsilon, just like that. That's going to all be in there. And then we, of course, have this term as well. So it's going to be plus square root 1 minus alpha t epsilon, just like that. Good. So now let's just go ahead and do the math, right? And it's just simple algebra now. We're going to distribute everything across. So this is going to equal to the square root of alpha t, square root of alpha t minus 1, x t minus 2, plus square root alpha t, square root alpha t minus 1, epsilon, plus, again, we just have this term left, so square root 1 minus alpha t, epsilon. So all we did is distribute, nothing crazy. And now what I want you to look at is this. This is a normal distribution with epsilon is 0, right? The mean is 0, and we're multiplying by a constant, right? So that means it's a normal distribution with mean 0 and variance of, just like before, in this case will be alpha t minus 1. right? Just like that. And actually, I believe I missed, yes, it should be 1 minus alpha t minus 1 here. My bad. So it should be 1 minus alpha t minus 1, which means you'll also be 1 minus alpha t minus 1. And that finally means you'll also be 1 minus alpha t minus 1. So this is a normal distribution that comes from this distribution right here, right? And then this is, again, just a normal distribution, standard normal, multiplied by a constant. Again, this will be a normal distribution with mean 0, and it's going to have a variance of just 1 minus alpha t. So again, we're using that variance property from before, right? Same variance property. The variance of something times epsilon is the square of the variance, or square of the constant times the variance of epsilon, which in this case is just 1 times the square of this, and the square goes away and we're done. Now, if you remember, we have another property for Gaussian distributions. That's that normal mu, let's say mu1 sigma 1 squared, plus normal mu2 sigma 2 squared. What's the sum of two Gaussian distributions? Because that's what we're doing here, right? We're doing the sum of this Gaussian distribution plus the sum of this Gaussian distribution. So the sum of two Gaussian distributions. Okay, well, this is going to be normal. Oh, sorry. It's going to be normal mu1 plus mu2 and sigma 1 squared plus sigma 2 squared. So again, this is another property of Gaussian distributions. Okay, if that's the case, all we need to do is sum up the means and the variances, right? So this is the sum of a normal 0, alpha t, 1 minus alpha t minus 1. Let's write a little bit better. Alpha t minus 1 plus normal 0, 1 minus alpha t. So all we need to do is add these together. So that's going to be a normal. 0 plus 0 is just 0. And then this one, we can just go ahead. It's going to be alpha t, 1 minus alpha t minus 1, plus 1 minus alpha t, 1 minus alpha t. And that gives us our final form. We can do a little bit of simplification though, right? Because this is going to end up being normal, 0 stays 0. We can distribute. This is going to be alpha t minus alpha t minus 1 plus 1 minus alpha t, right? We just went ahead and distributed, which means this alpha t here and this alpha t here will cancel. And we'll finally end up with normal 0, 1 minus alpha t minus 1. And that's the key idea. Now let's just go ahead and rewrite this in our final form. We can write this as basically epsilon, which is standard normal, times the square root of 1 minus alpha t minus 1. Now let's write that a little bit better. So it's going to be the square root 1 minus alpha t minus 1 epsilon. For again, the same reason as before. Epsilon is a normal 0, 1. If we multiply by a constant, that means the variance is going to be the square of that constant times the existing variance. So it's going to be 1 times the square of this, which is exactly this, right? It's because it just removed the square root. So we're just rewriting it in the kind of the form that we want it rather than as a distribution. So you have to be a little bit flexible of the notation here, but these two things mean exactly the same thing, right? Good. So now that we have that, let's go ahead and we can wrap it up and write the final form. So what we did, let's kind of scroll up a little bit. We had this term already, right? So that term's fine. And we just took these two terms here, combined them, and created this one term here. That's equivalently exactly the same thing. So let's just go ahead and put it all together, and then you'll see the pattern start to emerge. So that means xt is equal to, and this was already there from before, square root alpha t, square root alpha t minus 1, and it's going to be x t minus 2. So that was already there from before, right? And then we have this new term plus all of this stuff here. So plus square root 1 minus alpha t minus 1 epsilon, just like that. And now what you could do is you could also write the xt minus 2. So remember what we did up here. We took xt, and xt had a xt minus 1 in it, which means we could then write xt minus 1 and plug it in. But then we could also write xt minus 2 is equal to the square root of 1 minus beta t minus 2 xt minus 3 plus square root beta t minus 2 epsilon, just like we did before, and then plug this xt minus 2 into here, right? And then again solve. And if you do this over and over again, you'll kind of get to the end, and you can already start to see the pattern kind of emerge here. So let's just go ahead and write the final form here, just so it's clear. What we're going to do is if we kept going, right? Let's say we kept going, then you would get square root alpha t, square root alpha t minus 1, square root alpha t minus 2, let's write that a little better, alpha t minus 2, dot, 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 and then like square root alpha 1, right? So we're going to get all of this times x0, right? Because we're going to repeat this over and over again for all t. And this will be plus square root 1 minus alpha t minus 1, alpha t minus 2, dot, 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 alpha 1, right? We're going to go ahead and do all of them, times epsilon. And so that means we can finally write this if we had just, recursively kept writing the xt minus 2, xt minus 3, xt minus 4, all the way to x0, our starting image. And so now that we have all of that, we can go ahead and just write this in one nice compact form. And this is written as q xt given x0, right? Because given x0, we're writing a form for xt. It's going to be the product from I equals 1 to t of the square root of alpha I, just like that, and it's going to be times x0 plus the square root of 1 minus the product, again, I equals 1 to t of alpha I times epsilon, just like that. So we've just, wrote it in a product form. But didn't we just have, and actually one more thing, the product of a square root is the same as the square root of the product. So there we go. But didn't we just write some notation a little bit earlier? We wrote that the product of your alpha t's is just called alpha hat t, right? So the product from 1 to t is just alpha hat t. And this is why we have the notation. It's just shorthand. So that means we can rewrite this as alpha t, or square root of alpha hat t, right? Because we're doing the product from 1 to t, x0 plus our square root of 1 minus alpha hat t epsilon, just like that. And this is our final form for how we derive the adding t steps worth of noise to our original image x0. And that's the key idea. So now if we go back to the paper, you'll see that's exactly what we have. It looks like they write it in the normal distribution form, so we can actually put it like that. Again, this is a noise value, right? This is noise. That's normal, 0, 1. And you're multiplying it by a constant, and you're adding a constant. So let's just go ahead and shift it. That means this is going to be a normal distribution with mean of the thing we added, because we start with 0, so it's going to be 0 plus whatever this is. So it's going to have a mean of square root alpha hat t x0. And the variance is going to be the square of the thing we multiplied epsilon by. So that's just going to be 1 minus alpha hat t, just like that. So again, both of these things are equivalent to each other, which is why you'll see that notation here, right? The mean is just square root alpha hat t x0, and the variance is 1 minus alpha hat t. And we are good to go. And I is just an identity function, right? Or not identity, but identity matrix, because it could be a multivariate, covariance, that sort of stuff. So, okay, good. So we now have our first step done. We have been able to, so this is exactly what it is. A notable property of the forward process is that it admits sampling xt at an arbitrary time step t in closed form using this notation, right? So it's just a little shorthand that we use. This is equivalent to having done what we had done before, right? But this would have been, we'd have to go from x0 to x1 to x2 to x3 to dot, 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 right? So we have to repeat the step over and over again, all the way up to, let's say, x100 if we wanted to go there. So using this formula, we could have done that. We could have done one step at a time and added noise, and it would have been fine. Or we can go from x0 straight to x100 using the second formula that we had then, right? So it allows us to add 100 steps worth of noise without having to actually for loop through all the different steps. So just a little convenience, obviously not necessary, but it is how we'll implement it, because when you're training neural networks, all these operations happen millions and millions of times. So any little bit of efficiency we can add ends up kind of adding a lot of cost savings at the end. So that's the easy part for diffusion, because adding noise to an image is not all that big of a deal. The tougher part is for the model and for the derivation is the reverse diffusion process. And so now let's go ahead and begin reverse diffusion. Reverse diffusion. So again, remember, the goal of reverse diffusion is to take some time step xt worth of noise, like some image has already been noised to xt, and we want to just go back to xt minus 1, right? We want to denoise the image, and that's the main idea that we want to perform. So although that's great, there are a couple of problems that we need to face. So the way we write this, right, will be q xt minus 1 given xt, because we're given xt and we want to move back to xt minus 1. That's the key idea. The problem is this is actually not a tractable problem, because if we actually write this out, there's something that's still missing, and that's x0. Where's the data, the original data, which is x0? Well, it's not here because it's actually been hidden away. So can we show it? Yeah, we actually can. So we can take the integral of q xt minus 1 comma x0 given xt dx0. So what did I just do here? The marginal, so me taking this, right, over x0, me taking an integral over my image space, or data space, x0, the original data, marginalizes x0 out and only leaves us with this form here, right? So this is your standard marginal distribution. So if you don't remember, the integral of the probability of p, or let's say, let's do some joint distribution of j and I over I is equal to the distribution of just j, right? So this is your, this is called the marginal. So again, if you are unsure about that, you can go ahead and take a look in just a basic stats book. You'll kind of see that see this at the beginning, but this is a marginal distribution, right? So in the same way, we're just kind of going the other way here. I'm just saying that if I have this distribution here and I integrate over x0, right, my data space, then I'll end up with what I want. The problem is this is not solvable. How do you integrate over a super high dimensional unknown data space? Like if our images are 256 by 256 by 3, that's a lot and a lot of dimensions to integrate over. And this is not even a large image, right? We could go to even larger dimensions. And so we have some problems now, right? There's no way to actually solve this. And so this is intractable. And the reason is, again, because we have to integrate over the data space. So the simplification, or the assumption we do, is we say instead of this, we're going to do q xt minus 1 given xt and x0. So instead of having x0 kind of floating around here in something we want to solve that has to be integrated out, why not just include it in our conditional? So if we condition on x0 as well, which is our input image, now we want to compute xt to xt minus 1 for a specific x0, rather than just the general data space 0, like all the possibilities that x0 could be. We want to compute it for a specific x0. And so this is why you'll see that the learning the reverse process is only tractable when we add this additional conditioning kind of with this x0. Otherwise, it's not possible to solve. So let's go ahead. There's more details to that, but I'm not going to go too much more into it. But let's go ahead and just solve it, right? So this is what we want to solve for now. That's our key goal. So let's go ahead and do it. We're going to do q xt minus 1 given xt and x0, right? Because that's what makes it solvable. Now, anytime you see something like this, well, you say, well, I don't know how to go from xt to xt minus 1, and so this is a great time to just whip out Bayes' rule, right? So why not use Bayes' rule? So this is going to be, if you don't remember, let's kind of write it. This is probably a and b, and the x0 is just an extra conditioning, so that'll just be added to all of the distributions we'll be looking at. But if you remember, the probability of a given b is equal to the probability of B given A times the probability of A divided by the probability of B, right? That's your base rule, so hopefully you already know that. So all we need to do is the probability of A given B, so let's write that. So it's going to be Q. So the first one's going to be B given A, so it's going to be Q. B given A, so that's going to be XT, given XT minus 1, and X0 is kind of just hanging around there. So we're going to leave it alone. It's in the conditional. Times probability of A, that's the XT minus 1, and the X0 has to stay there, so it's going to be Q. XT minus 1 given X0. And then we're going to divide all of this stuff by probability B, which is just XT, and then the X0 kind of just hangs around. So it's going to be Q XT given X0. So there we go. That is our Bayes rule setup. And now you should start to see elements that we've seen before. We know how to get from X0 to XT. That's no problem, right? We just solved for that. That's exactly what we did earlier. How do you get from X0 to XT, right? We just solved for that. So we have that. Similarly, we know how to get from, so if we know how to get from X0 to XT, we also know how to get from X0 to XT minus 1. It's an indexing thing, right? And in the very first part, we solved how to get from XT minus 1 to XT. So we have kind of everything we need to solve this. We have everything we need. Now, to solve this, it's more tedious to write out. So let's just go ahead and write a recap here. I'm going to break it up into all three of them. And we'll just kind of write all the expressions out, put them together, and you'll see it becomes kind of messy, but then I'll try to simplify it down as quick as possible. So it's going to be Q. So the first one is XT given XT minus 1. And we kind of have this X0 here, but it doesn't have any purpose here, because to get from XT minus 1 to XT, we don't really care about X0 in our situation. So this, if you remember, was equal to, it was a normal distribution, and we solved for this earlier, was XT. It's just, that's the variable, so that's fine, XT. And it's going to be the square root of 1 minus beta t, XT minus 1, and then beta t, right? So that's what we had before. We solved for this, right? Let's kind of recap up here. It was right here, right? So it was a normal 1 minus beta t, xt minus 1, beta t. So we solved for this. We did this earlier, so it's nothing new. It's just rewriting something we had already. But we had that extra new notation now where 1 minus beta t was alpha t, remember? So we can just rewrite this as normal. Xt is our variable, and it's going to be the square root of alpha t x t minus 1. And we'll just leave beta t as beta t for now, just to keep it simple. Good, so that's the first one. And then, so that's number 1. And then we have number 2. That's going to be Q, and this was going to be XT given X0. So let's do the denominator one first, and then the numerator is going to be X0 to XT minus 1, so it's going to be the same thing. So let's do XT given X0, just like that. And to do this, we just solve for this, right? So that's just normal. It's going to be XT, our variable, and it's going to be square root alpha hat T X0, and 1 minus alpha hat T. Right, so we just solved for this. That was this step right here, right? So we just solved for that. So we have everything we need. And then similarly, 3, Q, xt minus 1 given x0 is exactly the same thing. It's just instead of having all these t's here, we'll have t minus 1s instead, right? Because it'll just shift over. So t minus 1 is our variable. We'll have square root alpha hat t minus 1, x0. And then we'll have our 1 minus alpha hat t minus 1, but nothing else changes. And so we're now good to go. Now we actually need to multiply and divide all these things together, and this is the part that gets kind of messy. So let's kind of remind ourselves, these are all normal distributions, and we have their means and standard deviations, and if they're all normal distributions, then we know exactly what a normal distribution looks like, right? A normal distribution is, let's say you had some normal mu sigma squared. That's just going to be 1 divided by square root 2 pi sigma squared, just like that. And then it's going to be e to the power negative 1/2. And let's just write out kind of the way we're going to be writing it, x minus mu squared over sigma squared. So that's our standard kind of normal distribution form. And so what we have is a normal distribution for each one of these things. And we're going to have to set up 3 of these expressions with their corresponding means and standard deviations and means, and then just write it all out. And this is honestly very annoying to write, but let's just go ahead and write all of it out. So the first one's going to be xt given xt minus 1 and x0, but that we don't really care about that right now. So that's going to be this form right here with this mean and this standard deviation, right? That's what we have. So it's going to be, let's write it. So it's going to be equal to 1 over, and let's try to write it a little bit smaller in case it takes up more space, 1 over square root 2 pi. And what's our sigma squared? Let's take a look. Our variance is beta t, right? Variance is beta t. So let's go ahead and write that. Variance is beta t, e to the power negative 1/2. And then we have x minus, what's our mean? Our mean was alpha hat t, square root of alpha hat t, xt minus 1. That was the mean. So that's going to be x minus square root alpha hat t x t minus 1 squared divided by our variance squared, which again was just beta t. So we had that. So that's the first one. That's number 1. Now for number 2, right? That's going to be this one here, xt minus 1 given x0. Okay, so that's going to be this one right here. It's going to have a mean of this and a variance of this. But other than that, all the other parts of the formula are the same. So we're going to write 1 over square root 2 pi, and then sigma squared, the variance, will be the square root of alpha hat t minus 1 x0, just like that. And then we'll have e to the power negative 1/2. And we'll have x t minus 1, right? Because again, the variable here is t minus 1. That's the variable because we're going to t minus 1. It's going to be x t minus 1 minus the square root of, again, our mean is square root alpha hat t minus 1, x0, alpha hat, sorry, this is my bad. This was the variance here. So it should be 1 minus alpha hat t minus 1, 1 minus alpha hat t minus 1. And that means the denominator here is going to be 1 minus alpha hat t minus 1. And the mean is going to be the square root of alpha hat t minus 1 x0. And this whole thing is squared. And so that's the second term. Again, as you can see, it just looks very messy. But we're going to simplify this down pretty quickly because we don't actually care about a lot of these terms. So let's go ahead and write out the denominator. The denominator is going to be, again, 1 over square root 2 pi. And remember, the denominator is going to be x0 to xt. So that's going to be exactly like this term right here. It's just instead of using xt minus 1, we'll have xt. So nothing else really changes, so we can just copy it. So it's going to be 1 minus alpha hat t, just like that. And then it's going to be e to the power negative 1/2 x minus square root alpha hat t x0 squared divided by 1 minus alpha hat t, just like that. And so this is the big expression that we need to now simplify down. And that's basically where our efforts are about to go. So first of all, something I want you to keep in mind is that all of these things are normal distributions. And in a normal distribution, this part here is called the Gaussian kernel. It's basically the kernel function for the Gaussian distribution. And this is just a normalizing constant that makes sure that this whole thing integrates to 1, right? So that just ensures that the thing integrates to 1, so it remains a probability distribution, right? Because the sum under a distribution, or the sum of the probability, should always sum up to 1. And so these are just those. And all of the stuff in there, we have alpha hats, and we have alpha hat, and we have beta, and then the 2 pi's, of course. These are just constants. So everything, all of this stuff here are just constants, and we can kind of assume that the math works out. And we'll just ignore them, right? Because it just makes the math a little bit simpler if we don't have them. So then what we're really left with is e to the power something times e to the power something divided by e to the power something, right? 3 exponents. And if you remember, if we have e to the power a times e to the power b divided by e to the power c, that's the same as writing e to the power a plus b minus c, right? That's totally fair. And so let's go ahead and do exactly that. We're going to just kind of pull it all apart and write it all out. And so how we're going to do this is we're going to just do, let's just do the exp notation to keep it simple. So we're just rewriting it basically. We're just writing the exponents. So it's going to be exp, and let's write an equal sign, equal to exp. There we go. And every single one of these terms, right, it's going to be all of this stuff plus all of this stuff minus all of this stuff, which is fine. But remember, all of them have a negative 1/2 in the front, as we see. So negative 1/2, negative 1/2, negative 1/2. Let's just go ahead and just take it out, just for simplicity. So we're going to pull a negative 1/2 out right at the beginning. And once we do that, we can then write the rest of it. So it's going to be xt minus square root alpha t x t minus 1 squared over beta t. That was the first one. Plus the second one was x t minus 1 minus square root alpha hat t minus 1 x 0 squared over 1 minus alpha hat t minus 1. So that's the second term. And then the third term is in the denominator. So we subtract xt minus square root alpha hat t. And then we have x 0 squared over, again, same thing, 1 minus alpha hat t. Yeah, so that should be good. And so that kind of just pulls it all together. So that's what we have. It's e to the power of all of this stuff. And now we will ask one more question just to make the math a little bit simpler. What do we want? We want to solve for q of x t minus 1 given xt and x0, of course. Which means really what we care about is the xt minus 1 values, right? Wherever we see xt minus 1, anything that's not xt minus 1, so xt and x0, are just constants. They're given to us, right? This is stuff that's given to us. We're given the initial picture, and we're given the noised time step that we want to denoise, one of those time steps. And so if we have this, then why not go ahead and just simplify it, just kind of removing all the stuff that's not xt minus 1, because anything that's not xt minus 1 doesn't really matter to us. It's just some constant that exists. And of course they matter, but in terms of the math, they don't actually make any difference. So we're just going to go ahead and get rid of them. And so to do this, what we need to do is let's go ahead and kind of write this all out. We have essentially 3 equations here again. 1, 2, 3. And so let's just take the numerators for each one of them and just break them out. So the first one is going to be, let's just do it down here. So the first one is going to be 1. It's going to be, what was it? It was xt minus square root alpha t x t minus 1 squared. Right, so that's our what we had. And so let's just go ahead and do a minus b all squared is a squared minus 2ab plus b squared, right? Standard formula. It's going to be xt squared minus 2, and let's put the square root of alpha t first. So square root of alpha t xt minus 1 plus b squared, which is just going to be alpha t x t minus 1 squared. So that's our standard a squared minus 2ab plus b squared formula. And let's just repeat this for all the terms. So we're going to have the second term. And of course, let's make it clear. All of this stuff was divided by beta t, which means all of this stuff was also divided by beta t. The second term, we're going to have, let's see, x t minus 1 minus the square root of alpha hat t minus 1 x0 squared, right? That's what we had. And it was divided, of course, by the constant. It was 1 minus alpha hat t minus 1. That's what we had. So let's go ahead and just kind of distribute it out. Again, it's going to be x t minus 1 squared minus 2 times square root alpha hat t minus 1. And then we're going to have x t minus 1 x0. So just like that. And then we're going to have plus b squared, which is going to be alpha hat t minus 1 x0 squared. So that's our second term. And of course, all of this stuff is divided by 1 minus alpha hat t minus 1. And now we have our third term. this is again going to be exactly like this top one here. It's just going to be xt minus square root alpha hat t x0 squared divided by this is going to be 1 minus alpha hat t, just like that. And so this is again going to be xt squared minus 2 square root alpha hat t xt x0 plus no more square root, we square it, it's just going to be alpha hat t x0 squared. And again, of course, all of this is going to be divided by 1 minus alpha hat t. And so these are our 3 formulas that are added together. Remember, there's basically 3 of them, right? And they're just all added together. And now here's basically what we're going back to. We really just care about the xt minus 1 terms, because they're the terms that, they're the terms in our expression, what we want to find the expression for, which means xt and x0 here, I mean, they're important, but they're just extra, like they're constants, right? They're just constants in our thing. And so why not just ignore them? Because the constant doesn't really affect what we're trying to find here. And so what we want to do is just identify where do we see the xt minus 1 term. And what we see is we have an xt minus 1 here on this term here. We have an xt minus 1 squared here, so we have that. We have an xt minus 1 squared here. We have an xt minus 1 here. But notice everywhere else, there's no more xt minus 1, which means this whole expression right here is just some constant, right? Just some c. And then this part of the, or not that part, but basically, if we rewrote this as like, let's do xt minus 1 minus 2 square root alpha hat t minus 1, xt minus 1 x0 over 1 minus alpha hat t minus 1. That's the first part. Plus, now we have this second part. It's going to be alpha hat t minus 1 x0 squared, again, over 1 minus alpha hat t minus 1, because I just took this denominator and I divided on these 2 terms first, and then I divided this term and just added them together, right? So that's fair game. That's me. Let's write basically what it is. A plus b plus c over d is equal to a plus b over d plus c over d. That's fair game. I'm allowed to do that. So this term is what we care about. This term has no xt minus 1, so it's just a constant. It's again just a constant. And then similarly, xt squared divided by beta t is also just a constant. So let's just keep only the terms that we care about and just kind of group all the constants together into some like, oh, it's just a constant. Let's not worry about it. So to do that, what we need to do is just rewrite it. And so what we're going to do is just keep these terms that we care about in the expressions, and anything that we don't care about, we're just going to ignore them and just stick it in some constant term at the end. So what that's going to look like is kind of like this. So it's going to be equal to exp. Again, remember, we have the negative 1/2 from before, so that's still there. And then what do we have? We need the negative 2 alpha hat square root alpha hat t minus 1 xt minus 1 x0, and we have this alpha hat, or sorry, not there. Let's start at the top, this one right here. We have this term right here, minus 2 square root alpha alpha t xt minus 1, and we have this term right here, alpha hat xt minus 1 squared. And then in the second one, we're going to have this term right here and this term right here. But everything else we can just kind of ignore, right? We can kind of just ignore u and ignore all of u and just stick it into some constant term at the end. So to do that, let's go ahead and just write it out. It's just simple as minus 2 square root alpha t. Let's write that a little bit better. Square root alpha t xt xt minus 1. And then we're going to have plus alpha t xt minus 1 squared, right? Because that's what I had. I had alpha t xt minus 1 squared, and I had minus 2 alpha square root alpha t xt minus 1. So I just rewrote it down here. And of course, all of this stuff was divided by our beta t from earlier. We have plus the second term. We're going to have xt minus 1 squared minus 2 square root alpha hat t minus 1. We'll have an x0 xt minus 1. And then, of course, we had the 1 minus alpha hat t minus 1. And then we just have some plus c at the end. And this c is some constant made of alphas, betas, alpha hats, x0, and xt. It's basically everything that we didn't care about for our the non-xt minus 1 terms. And so this is what we're dealing with, and that constant is just kind of going to exist there, and we're just going to ignore it because it doesn't affect anything. So we are almost good to go, but let's kind of recognize something here. We have a xt minus 1 term here and here, and we have an xt minus 1 squared term here and here. So why not just rewrite it kind of like a quadratic, and we're going to see that come together right now. So this is going to be equal to exp negative 1/2. And first of all, we have, let's do the xt minus 1 squared term. So we're going to do an xt minus 1 squared. And what's going to be left? If we, again, remember, this is like a plus b over c is just a over c plus b over c, right? So I'm just splitting the fraction up. And so we have, if we have xt minus 1 squared, that means the first constant is going to be alpha t over beta t. So it's going to be alpha t over beta t. So that's the first one. Plus xt minus 1 here, or xt minus 1 squared here, has a constant of 1 in the front, right? So it's just going to be plus 1 over 1 minus alpha hat t minus 1, just like that, right? So all I've done is just take the terms apart and regroup them like this. So I took this right here from xt minus 1, and I took this right here from this xt minus 1 squared, right? So we got both of those. And then similarly, we're going to do plus xt minus 1, so not squared. Xt minus 1 is paired with a negative 2 square root alpha t xt and a negative 2 square root alpha hat t minus 1 x0 xt minus 1, right? So if that's the case, we have this negative 2 term on both of them. So there's no reason to keep it inside. We can pull it out. So we can replace this with negative 2 x t minus 1. That's what we're taking out. And then we'll be left with just the square root alpha t xt over beta t plus square root alpha hat t minus 1 over, and then of course x0 over 1 minus alpha hat t minus 1. And then we still have the plus c kind of constant at the end that we don't really care about. So there we go. That's just me taking these variables and regrouping them. I didn't do anything fancy. I've just regrouped them. Just take a close look at it. You'll see that it kind of works out. That xt minus 1 here, xt minus 1 squared, is multiplied by this and is multiplied by this. So I can group those together. Right? I'm just taking a common. And then xt minus 1 and xt minus 1 is grouped by, again, this, and it's grouped by all of this. So again, we can just group those together and rewrite it like this. And what you'll notice is we now have a quadratic. We have a x squared times something minus 2. So we have essentially, so let's write it that way. This is some a, and this is some b, and that's some constant c. It's literally a quadratic, right? It's just a simple quadratic function. And so if this is a quadratic function, it looks kind of like this, right? It's going to be a xt minus 1 squared minus 2 b x t minus 1. And then it's going to be plus c, right? There's a plus c there, but again, we're just going to ignore that plus c for now. We don't care about it. We'll deal with it later. Now, this looks all well and good. It's a quadratic, so this is a quadratic in xt minus 1. But this is not a very helpful form to us. So to get this to look like what you'll see in the paper, we have to do something called completing the square. So again, if you don't remember what completing the square is, you learned all about it in your basic algebra class. But completing the square is just us trying to get this to look like a minus b whole squared. So if I want to do a minus b whole squared, which is equal to a squared minus 2ab plus b squared, right? I just need to figure out how do I get this to work. So let's take a look. We have something squared. So this is our a xt. Okay, so let's actually make this a little bit simpler for us. So we can first do a. Let's pull an a out. And then we're left with x t minus 1 squared, right? Because we pulled an a out, minus 2 b over a x t minus 1. That's fair game. Again, we're just ignoring the c, right? It doesn't matter. So just forget about it. So we are pulling, if we pull an a out of this expression, then we pull the a out of here. And then because there's no a in here, we have to divide by an a to compensate for it, right? So we're good to go there. This is fair game. Let's complete the square on this expression here, just because it's a little bit simpler than actually doing it with the a included. So we have something squared minus 2 times something, and we just need to add something to get this to work. So let's say we do a, leave that alone. This is x t minus 1 squared minus 2a, which is x t minus 1, and then b is b over a, right? It's going to be a squared minus 2ab, or let's pick a, let's pick something else. So do m squared minus 2ml plus l squared, right? Just so the variables are a little bit different. So we'll end up with a m squared, which is our x t minus 1 squared. So that's fine. And we have the negative 2 shows up, right? Negative 2 and negative 2 is good. And m shows up again, right? X t minus 1. Instead of x t minus squared, it's just x t minus 1. And we have this l, b over a, which means l squared would be plus b over a whole squared, right? That's fair game. Now, the thing is that if I add something to my expression, I of course have to also subtract it, right? Just to compensate, so we're not adding something that wasn't there. And this will let me complete the square, because all of this is just, so it's going to be equal to a times x t minus 1 minus b over a squared, right? It's x t minus 1 squared minus 2 times x t minus 1 beta b over a plus b squared, which is going to be b over a whole squared. That's exactly what we have here. That creates this. And then we, of course, have this minus b squared over a squared extra term kind of dangling there. And we can go ahead and just multiply it through. So it's going to be a times xt minus 1 minus b over a squared minus b squared over a and a squared will cancel here. So we'll just be left with a. So b squared over a. So we're good to go there. And so now we have effectively completed the square. Now let's remind ourselves, what was a and b? A is made of a bunch of alphas, betas, alphas. Okay, so everything in A is a constant. And B is made of alphas, betas, alpha hats, and it's made of xt and x0, which are given to us. So they're also constant. So everything in A is a constant. Everything in B is a constant. And if you again remember, we have a, we didn't really include it because we never cared, but there's technically a plus c here as well, some constant. And if this is a constant and this is a constant, then that we don't really care about, then why not just go ahead and rewrite all of it as just one big constant again, right? We just did some new constant, but whatever, it's just some c. We don't care. And so this means we can rewrite this whole expression, right? This whole expression here, and we're gonna write it in terms of a and b just to avoid writing these big expressions again. We'll get back to that in a bit. That means we're finally back to, let's change back to orange. It's gonna be, let's write a little bit more in. It's going to be equal to exp negative, so it's going to be negative 1/2, but we have this a as well, so it's going to be negative a over 2. We have our x t minus 1 minus b over a squared, and we have that c that we just don't care about. So there you go. So we went ahead and rewrote all of this stuff here in terms like this by completing the square. And because we completed the square, this is the a in our completed square, and this is the b in our completed square. And so what's left is to figure out basically what we had, but there's actually one more important step we need to do before we do that. Let's rewrite this in one other way. Let's do exp. Instead of writing minus a over 2, let's write minus 1 over 2, and let's write our xt minus 1 minus b over a squared over 1 over a. So that's fair. I took the a here and just moved it to the denominator as 1 over a because it's the same thing. And we have the plus c, but again, that's fine. What does this look like? This is e to the power negative 1/2 x minus something divided by something. Well, this is exactly our Gaussian, right? Gaussian kernel, right? Gaussian kernel. And there's a square here, of course. And how do I know that? Well, we just wrote it, right? We wrote that a second ago. The Gaussian distribution, where did I write it? We wrote it, wow, there's so much math here. All right, we wrote it right here, right? E to the power -1/2 x minus something squared divided by something is our Gaussian kernel. And this was just the constant in front that exists just to ensure that this thing integrates to 1. And those constants are still there, right? We still have, remember, we just ignored the constants. We had all of these extra constants from earlier, right? All of these existed. We just ignored them because they're just constants that kind of make sure things normalize to 1. So there are still constants there, which means this is a Gaussian kernel, a standard Gaussian kernel. It's just multiplied by some constant, right? Because again, e to the power a plus b is e to the power a times e to the power b. So we're multiplying by some constant. We don't really care about this c, right? It's just going to be another normalizing constant that gets merged in somewhere else. So let's just look at this piece right now. And so if this is a Gaussian distribution, and so let's also write, this is our expression for q xt minus 1 given xt x0, right? That's what this is. That's the Gaussian distribution that describes this, which means this is the mean, right, of the Gaussian distribution, and this is the variance of the Gaussian distribution, because that's our Gaussian distribution formula, right? It has to be that. It can't be anything else, because it's e to the power x minus mu squared over sigma squared. So this is our mu, mean, b over a, and this is our variance, 1 over a. Okay, so let's go ahead and just find our final expressions for these two things, and we will be done. That's a little bit, it made it sound simple. It's a little bit more work to go, but the best place to start, let's start with the variance, 1 over a, right? 1 over a, because we're going to need basically the mean is just b times 1 over a, so we can reuse that piece later. So let's just start with 1 over a, and then we'll get to the mean afterwards. And so our variance is going to be, and so actually, just to keep the notation correct, the variance they use for the reverse process, they use something called beta hat, or beta tilde maybe, right? Beta tilde is the reverse process variance. It's just their notation. This is our 1 over a that we care about. And so this is going to be 1 over, and we know exactly what a is. That's just what we had here, right? It's all of this stuff, or sorry, too big of a circle. It's all of this stuff right here. So let's just go ahead and do 1 over that, just like normal. And so it's going to be our alpha t over our beta t plus 1 over 1 minus alpha hat t minus 1. That's what we had. And to do the simplification, right, let's just go ahead and cross multiply and just do our simple simplification. 1 over, it's going to be, let's do alpha t 1 minus alpha hat t minus 1 plus 1 times beta t is just beta t divided by the product of the denominators, right? Beta t 1 minus alpha hat t minus 1, or just adding the fractions together. And 1 over this is just the reciprocal, so that's just going to be our beta t 1 minus alpha hat t minus 1 divided by alpha t 1 minus alpha hat t minus 1 plus beta t. And there we are. That's everything we need for this. Now we can actually simplify this quite a bit. And to simplify it, we have to remember one fact, or just kind of do an extension on a fact that we talked about. Alpha hat t is the product, right, from I equals 1 to t of our alpha I. This is the same as writing, if we pulled out one of the alphas from this product, we could rewrite this as alpha t times the product of I equals 1 to t minus 1 alpha I. That's fair game, right? Because if this is the product of all the alphas from 1 to t, that's the same as doing all the product of all the alphas from 1 to t minus 1 and then multiplying by alpha t afterwards, right? So it's all the same thing, which means this is the same as alpha t alpha hat t minus 1. So this would be the product of everything from 1 to t minus 1 times just the alpha t. So it's just a notation thing, right? Which means we can now simplify a little bit. So this is going to be equal to, let's see. Let's just do the denominator here. So alpha t 1 minus, so it's going to be alpha t 1 minus alpha hat t minus 1 plus beta t. That was our denominator. So that's going to be alpha t minus alpha t alpha hat t minus 1. So we just see that appear right there. And we, of course, have our beta t. And so that's going to be equal to alpha t minus just a alpha hat t, right? Because this is a product up to all terms from 1 to t minus 1. And then we have the tth term. So that's just all of them up to t plus beta t. So that's looking pretty good there. But remember, we have the other property that we leveraged earlier. Alpha t is equal to 1 minus beta t, right? It was defined this way. I didn't create it. There's no proof. It's just defined this way. Let's just rewrite this beta t in terms of alpha t. So that means beta t is going to be 1 minus alpha t. So that's going to be alpha t minus alpha hat t. And it's going to be plus 1 minus alpha t. Nice. That means this alpha t here will cancel. And we are just left with 1 minus alpha hat t. And so that is our denominator. And then we, of course, have the numerator still from earlier. So we can just go ahead and rewrite all of it together as our variance. Beta hat, the reverse variance for the reverse process, beta hat t, is going to be equal to 1 minus alpha hat t minus 1 over 1 minus alpha hat t beta t, right? So this beta t is from our noise scheduler. So that's based on our noise scheduler. This beta tilde t is the reverse process, essentially, the reverse variance that we're looking for. And so this is a very, very, very important equation. And we see it show up right here in the paper, right? So if you scroll down just a little bit more, you can see right here, beta tilde t is 1 minus alpha hat t minus 1 over 1 minus alpha hat t times beta t, which is exactly what we got. So it's looking promising. Looks like we're on the right track. Now we have one more step. We just computed the variance. Now we have the mean, right? B over A. And this one's a little bit more challenging. Not challenging in the sense that anything you write at this point would technically work. We could just use the original form for B over A. We just want to simplify it down to look like the form that they actually have in the paper, even though they're obviously equivalent, whether or not we simplify it or not. So let's go ahead and do, let's see here. So our mean, which they call mu t, is going to be b over a in our case, right? That's what we had, b over a, which is also b times 1 over a. And we already found 1 over a was beta tilde t. So this is really just equal to b times beta tilde t. Okay. And what was b? Let's remind ourselves. That was this part right here, right? This stuff right here was the b from before, right? That's what we said is b. So we just have to rewrite that and then multiply it by the beta tilde t, which sounds like a lot of work, and it actually is quite a bit of work to simplify down. So let's go ahead and write everything. So we're going to do, oh boy, all right. So alpha, square root alpha t over beta t xt plus square root alpha hat t minus 1 over 1 minus alpha hat t minus 1 x 0. Let's just make sure I copy that. So we have square root alpha hat xt over beta t, square root alpha t xt over beta t, and the square root alpha hat t minus 1 x 0, 1 minus alpha hat t minus 1. That looks like what I wrote. Yeah, alpha hat t minus 1. Good. And we, of course, have the x 0 as well. Yeah, the x 0 and an xt. Okay, good. We're fine. I think that's correct. So that is our b. And then beta tilde t, we just solved it, right? We just did it right here. So we just have to rewrite that again. So it's going to be times 1 minus alpha hat t minus 1 over 1 minus alpha hat t beta t, just like that. So that's our form. And now it is time to simplify. So we're just going to take all of this stuff and multiply it to the first term, all of the stuff, multiply it to the second term. So let's do the first term. That's going to be, we're going to have a square root alpha t times, the numerator is going to be 1 minus alpha hat t minus 1. So let's write that first. We square root alpha t. We're going to have a 1 minus alpha hat t minus 1. And then we have a beta t here, but we also have a beta t in the denominator. So those two things will cancel. So this beta t and this beta t will cancel, and we'll be left with just the 1 minus alpha hat t in the denominator. So 1 minus alpha hat t in the denominator, and we of course still have the xt. So that's us multiplying all of this by the first term. And then for the second term, we're going to have plus square root alpha hat t minus 1, that's here. And then all of this stuff right here is the same as all of this, so those two would cancel, and all we would be left with is the beta t term and our denominator. So it's going to be beta t over 1 minus alpha hat, alpha hat t, yeah, that's it, and then an x0, just like that. And so that does our entire second term. Nice. So that's our mean, and that's our expression, kind of just expanded out. And now we have a little bit of work to simplify this. So the first thing we want to remember that xt, so this is a reminder from before, xt is equal to, and we solved this, right? We did this earlier. This was, let's see where we wrote it. There's so much little math going on here. I think we wrote it right at the beginning. Yeah, here we go. Xt is equal to the square root of 1 minus beta t, xt minus 1, square root of beta t epsilon, and then when we recursively do it, we wrote the kind of the full form from x0. It's going to be the square root of alpha hat t x0 plus square root of 1 minus alpha hat t epsilon, right? That's the form for xt. That's how we get xt, depending on x0. So we're just going to rewrite that again. Let's just write it again, because we're going to have to rearrange that expression just a little bit. It's going to be equal to the square root of alpha hat t x0 plus square root 1 minus alpha hat t epsilon, right? That's what we started with. Now, what if we could just rewrite x0 in terms of xt? That would be convenient, right? Just having one variable rather than, or not variable, but just kind of having everything in terms of the same thing. So let's just rearrange. So we can also say x0 is equal to, it'll be xt minus all of this stuff here. It's going to be xt minus square root 1 minus alpha hat t epsilon. And then we're going to divide by this term, right? It's going to be 1 over square root alpha hat t, and there'll be a bracket around this whole thing. So there we go. I just rearranged it, right? So instead of the equation being in terms of xt, we wrote it in terms of x0. That's no problem. And then we can take this form for x0 and plug it in right there, just to make our life a little bit simpler. Not simpler yet, but I promise it will get simpler. So that means we have 1 minus alpha hat t minus 1. Let me see what I'm doing. So alpha hat t minus 1 square root alpha t divided by, we still have the 1 minus alpha hat t. So 1 minus alpha hat t minus 1 square root alpha t. Okay, everything's good there. And we have our xt. So there we go. And then similarly, we're going to have our all of this stuff here. So it's going to be the square root of alpha hat t minus 1. We're going to have the beta t here. Now again, beta t is just 1 minus alpha t, so might as well just rewrite it. So 1 minus alpha t, because again, this beta t is just 1 minus alpha t, so that's no problem. They're equivalent. They're defined that way. We have the 1 minus alpha hat t in the denominator. So there we go. And then we're multiplying this by this whole expression, right? That's what we're replacing x0 by all of this. So it's going to be times 1 over square root alpha hat t, and we're going to have xt minus square root 1 minus alpha hat t epsilon, just like that. And so now that we have all of that, it's time to start organizing a little bit and then simplifying down. So what you'll notice is we have some terms based on xt, and we have kind of some terms based on our epsilon. And I believe, I hope not missing anything. I don't think I'm missing anything. So yeah, we should be good. So we have some terms based on xt, we have some terms based on epsilon. So let's just go ahead and start organizing them all together. And so we can first take our xt, and we can group together all the stuff that has xt in it. So that's going to be all of this. It's going to be 1 minus alpha hat t minus 1. And then it's going to be all of this times the square root of alpha t divided by 1 minus alpha hat t. So that's the first thing that was with xt. And then the second thing that was with xt is plus. We're going to have the, it's basically going to be all of this stuff, right? Because we're going to multiply it with xt. So let's go ahead and write that out. It's going to be square root alpha hat t minus 1, 1 minus alpha t over 1 minus alpha hat t. And then we also have this square root of alpha hat t, right? So it's going to be square root alpha hat t. And so that's the first term. And that's just me taking my xt because I basically have right now something that looks like a times xt plus b times xt plus c. So what I'm doing right now is a plus b, so xt times a plus b plus b times c, right? bc. So I'm just grouping the xt together just like that. So we need to still do this third part, right? The epsilon term. So let's go ahead and write that. We're going to have plus, or minus in this case because there's a negative sign there. So minus epsilon, and we're going to have everything on the inside. So it's going to be all of this stuff times this thing here as well, right? We're going to have both of those things. So let's go ahead and just write it all out. Oh, went too far. So there we go. So the first one's going to be the square root of alpha hat t minus 1. Then we're going to have 1 minus alpha t. Then we're going to have square root 1 minus alpha hat t. And then in the denominator, we have 1 minus alpha hat t. And we have the square root, so we don't need the parenthesis here, the square root of alpha hat t. Just like that. So we have kind of two equations here, two really big equations here. We have this first equation, right? This is 1. And we have the second equation, which we'll call 2. And so now let's simplify each of these things down individually. So starting with 1, so we're going to solve equation 1 first, or simplify equation 1 first. Let's remind ourselves of, again, a couple of little facts. Alpha hat t minus 1 divided by alpha hat t is what? That's going to be alpha 1 times alpha 2 times ... alpha t minus 1, right? This is the product up to t minus 1, but this one's going to be alpha 1, alpha 2, ... alpha t minus 1, alpha t. This is the product up to t, which means these will all cancel and you'll just be left with 1 over alpha t. So that's the first one. And of course, the property from before that we just wrote out, alpha hat t is the same as alpha t times alpha hat t minus 1, right? We rewrote that earlier as well. So again, that comes from this. So can we go ahead and do a little bit of that simplification? And yeah, we actually can. So let's rewrite this equation here. It's going to be 1 minus alpha hat t minus 1 square root alpha t divided by 1 minus alpha hat t plus square root alpha hat t minus 1, 1 minus alpha t over 1 minus alpha hat t square root alpha hat t. So that's what we had from earlier, right? So that's all we had. Yeah, that looks all correct. And so what we're going to do now is we have a square root of alpha hat t minus 1 divided by square root of alpha hat t, right? So that's just this, right? So that's just going to be the square root of 1 over alpha t, right? So we can go ahead and write that simplification. This is going to be equal to 1 minus alpha hat t minus 1 square root alpha t over 1 minus alpha hat t plus the 1 minus alpha t stays the same. The 1 minus alpha hat t stays the same. And then we have again, the square root of this. Oops, let's write that better. The square root of all of this, right? Square root of alpha hat t minus 1 over the square root of alpha hat t is the same as the square root of this over here, right? So square root of 1, or just 1 over the square root of alpha hat t, which means we just have the square root of alpha t here. Sorry, I meant alpha t here. So square root of 1 over alpha t. Good. So now that we have that, that's our first major simplification. The next simplification will be on this portion right here. So we have 1 minus alpha hat t minus 1 times the square root of alpha hat. Okay, so what we can do here is cross multiply, right? We need to actually put these terms together. And so we have a 1 minus alpha hat t here, but we have a 1 minus alpha hat t square root alpha t here. So we need to introduce another square root alpha t in the numerator. So let's go ahead and do that. It's going to be square root alpha t times 1 minus alpha hat t minus 1 square root alpha t, that was there from earlier, divided by square root alpha t, 1 minus alpha hat t, those are there from earlier, and then we're going to do this part is the same, 1 minus alpha t over square root alpha t, 1 minus alpha hat t. So all of that is fine. And now we can see the denominators are the same, so we can actually add them together. But we also see that we have a square root alpha t, square root alpha t. So both of these will multiply together to make a single alpha t. So that's going to be equal to alpha t times 1 minus alpha hat t minus 1 plus 1 minus alpha t, right? Plus 1 minus alpha t divided by the entire denominator. So that should be fine. That's going to be square root alpha t 1 minus alpha hat t. So we're good to go there. Let's go ahead and actually distribute the alpha t in. So that's going to be alpha t minus alpha t alpha hat t minus 1. So we already see that property show up again. And we have plus 1. Let's write this a little bit cleaner. Alpha t minus 1 plus 1 minus alpha t. So that's going to disappear. And we, of course, again, divide by square root of alpha t, 1 minus alpha hat t, which means this term and this term will cancel. And so all we are left with is this part right here. This is going to be equal to 1 minus alpha t, alpha hat t minus 1 divided by square root alpha t 1 minus alpha hat t. But what was this? Alpha t times alpha hat t minus 1 is just alpha hat t. So that means, again, this is going to be 1 minus alpha hat t divided by square root alpha t 1 minus alpha hat t. And then this and this will cancel, and we are left with 1 over square root alpha t. So this whole giant expression that we started with, which looks crazy, ends up all disappearing, right? This first part of the expression, so we only dealt with part 1 here of the expression. This whole thing simplifies down to a nice and easy 1 over alpha t. So we're gonna box that up because we're gonna need that a little bit later. All right, now let's do equation 2, right? So equation 2. So that's going to be the second part of the equation, multiplying epsilon. It's all of this stuff right here. So let's go ahead and rewrite that and simplify that down. So that's going to be our, let's do it down here so there's some space. So this is going to be equation 2. This is going to be our, so let's just rewrite it, square root alpha hat t minus 1. We had a 1 minus alpha t, and we had a square root 1 minus alpha hat t. So there we go. And then in the denominator, we had a 1 minus alpha hat t square root alpha hat t. Let me double check that I copied that correctly. So we had divided 1 minus alpha hat t times the square root of alpha hat t. In the numerator, we had square root alpha hat t minus 1. Yeah, that looks correct. Okay. All the alphas have hats on them except for this one. Okay, good. Yeah, we're looking good. So I'm just going to make sure it's correct as we're going. Okay, so now that we have that, what we can do is a little bit of simplification here again. So if you remember, we have a alpha hat t minus 1 up here, square root of alpha hat t minus 1, and we have a square root of alpha hat t here. So that means if we divide them, we'll just be left with 1 over square root alpha hat t in the end. So this is going to be equal to 1 minus alpha t square root 1 minus alpha hat t, so that's still there, and we divide by square root alpha t, so that's going to be right here, alpha t, because we divided alpha t. So this is the product up to t minus 1. This is the product up to t. And so dividing them is just the tth term, just like we saw earlier. And we have our 1 minus alpha hat t here as well. Now, one more thing to notice is that this is like saying the square root of a divided by a. We have the square root of 1 minus alpha hat t and just 1 minus alpha hat t. So that's the same as writing 1 over the square root of a, right? We can simplify that. So this is then equal to, we can rewrite this. It'll be left with 1 minus alpha t divided by square root alpha t and square root 1 minus alpha t, alpha hat t. There we go. And so this is our second term. It's already done. So we now have the first term, we have a, and we have b. And so we had this term, we had xt times the first equation minus epsilon times the second equation. So let's go ahead and write all that out. So it's going to be, we had equal to it xt times the first equation, which we saw was 1 divided by the square root of alpha t, minus our epsilon times the second equation that we just got, which was 1 minus alpha t over square root alpha t square root 1 minus alpha hat t, just like that. And now that we have that, we have a 1 minus alpha t here, we have a 1 minus alpha t here, so let's just go ahead and take a comment. So it's equal to 1 minus square root alpha t, and this is now going to be xt here minus 1 minus alpha t over square root 1 minus alpha hat t epsilon, just like that. And this is our form for mu t. So that's our mean. And so what we ended up with is our q x t minus 1 given xt x0 is a normal distribution with mu t and let's say sigma squared t, or let's use the correct terminology, beta tilde t, where mu t is equal to all this stuff right here, 1 over square root alpha t, xt minus 1 minus alpha t over square root 1 minus alpha hat t epsilon. That's what mu t was. And our variance, our beta t, beta tilde t, was equal to 1 minus alpha hat t minus 1 over 1 minus alpha hat t beta t, where beta t came from our noise scheduler. And so this is our entire reverse process. And let's verify with the paper real quick, right? Let's make sure we got exactly the same expression as them. And we should have. We saw that, okay, so they actually wrote out the split equation. I wonder if they write the simplified equation here somewhere. I cannot remember. Oh, here we go. So it's 1 over square root alpha t xt minus 1 minus alpha t over square root of 1 minus alpha hat t times some error epsilon. And that is essentially the formula, right? That's basically what we derived right here, exactly right here. So equation 10 reveals that mu theta, right? So we'll see why it's theta later, must predict this thing here. And so this is where our equations come from. That's the main purpose of all of these equations. The main reason I wanted to do this again was just so when we start deriving and actually building the diffusion model in the next couple of videos, you are not completely confused of where do these formulas come from, because they look crazy and it's hard to kind of interpret exactly like where they came from just from looking at them. So that's the derivation. We spent almost an hour 45 here doing all of this math. So hopefully this is helpful. If you have any questions, drop it down below, but I will see y'all in the next one.